All right, my little linear algebra babies, we are back for another section, another video, and let's begin. So, where are we? Just kind of give you a snapshot. We are midway, well, not midway, but pretty close to midway through chapter 4. We're going to be tackling sections 4, 4, 4, 5. The topics are that of basis. That's where we're going to begin, and then we're going to move from basis to dimension. And I want to start with something that's going to look somewhat trivial, somewhat simple for the maths that you're at right now. But do me a favor, pay attention to this very, very easy example so that you can understand basis. So that when on the next example, we're going to switch it up a little bit for the problems that we are interested in. All right, so what's the idea? Why take time out of our schedules to worry about specifying a basis for a vector space, right? And the idea is we want to impose some type of coordinate system on our vector space. And I'm going to start. Let's start with something very easy. Let's start with the basis vectors v sub 1 and v sub 2, which are 1, 0, and 0, 1. Now, what I'm going to do right now is just go ahead and graph v sub 1. Okay, so this would be v sub 1. And I'll go ahead and graph v sub 2. So x is 0, y is 1. This would be v sub 2. Now, in this case, it is true that this set of these two vectors is a basis, or does form a basis for our vector space R2. And we're gonna come back to a couple things, but as of right now, I'm going to give you a point. Okay, I'm going to give you a vector. Let's make it 5, 4. All right, so now I completely understand that you know how to plot 5, 4. I know that you know how to go over 5 and up 4, but I'm not asking you to think about the normal plotting of points the way that we've done ever since probably middle school. Instead, what I want you to think about is the fact that if you attach a scalar to v sub 1 and you attach a scalar to v sub 2, if it is true that v sub 1 and v sub 2 form a basis for our vector space of R2, then what we would be saying is that we can reach any xy. I'm going to, instead of x sub 1, x sub 2, I'm going to use regular xy. It would mean that we can reach any point just from those two vectors. Ready? So now the point that we are considering is the point 5, 4. So let's rewrite this. So what you're going to see me do is just place all the vectors where they need to be. Now this is something you've seen me do many times, but here in just a second I want to show you the way we're going to think about the geometry of this. Ready? So let's go ahead and put everything in the right spot. Let's start with our vectors. So v sub 1 is 1, 0, and v sub 2 is 0, 1. And finally, the point, the vector that we are interested in is 5, 4. Okay, so this is our matrix equation or vector equation that we've seen many, many times. And if you recall, when when we're solving them, we're really solving for the scalars, right? The weights that you attach to the vectors. So there's got to be some weight, C sub 1, that you would scale to V sub 1, and there's plus some weight, C sub 2, that you would scale to V sub 2, such that when all is said and done, you get the vector 5, 4. Now, I'm going to go ahead and show you how you would approach this really quickly. It's just, well, actually, since this is such an easy case, let me just go ahead and get you to where I want you to be. It's simple enough that we know that we're going to move 5 in the x direction and 4 in the y direction. So this is what our linear combination looks like. And now what is more important is going to be the geometry of what's about to happen. So let me label V sub 1 under the vector V sub 1 and V sub 2 under that vector V sub 2. And now let's you and I think about how we get to the point 5, 4. Yes, I agree. We go to the right 5 and up 4. But do you see that really to get to 5, I'm going to try my best to hold my stylus here for a second. When we move to, do you see how really that is 5 V sub 1s, right? Of V sub 1 in this case is a unit vector pointing in the positive x direction. And notice that we need 5 of them to get to here. And then likewise, we would need 4. So including the starting vector, we need 4 total V sub 2s to get to the point that we want to reach. Now, of course, even a child can just navigate this XY coordinate system by moving to the right 5 and up 4, and there's their x. Now I want you to imagine something for a second. Let's assume that instead of having our basis vectors as 1, 0, and 0, 1, which I'm going to give those a name in just a second, these this form of a basis. But let's imagine now you were in, let's go back in time. So you're in middle school, you're sitting down, you've been plotting points like the points that we just plotted, where you move over 5 and up 4, and then all of a sudden your teacher brings you some new graphing paper, right? And in this case, the new graphing paper looks like this. All right, now I'll come back to what it is that I just skipped over in just a second, but stay with me. So interesting. So now you don't have these perfect 90-degree angled lines that running in the x direction and the y direction, but your teacher is still asking you to plot points with this new coordinate system, right? This new coordinate system. Well, where did this coordinate system come from? Because obviously we're still in R2. That has not changed. But this doesn't look like our regular XY coordinate system. So what happened? So stay with me. Let's see if we can figure out what just happened. So what we're going to do is we're going to change our basis vectors. So our new basis vectors, right, the new basis vectors that we're going to use is going to be the following 2 vectors. But now take a look at V sub 1 and V sub 2. So in fact, I've even plotted them for you. So you can see V sub 1 has been plotted and V sub 2 has been plotted. Now I plotted them the normal way for this. For right now, we went to the right 2, and then we went up 1 to get to v sub 1, and we went to the right 1 and up 2 to get to v sub 2. And now let's ask a question. Let's assume that your teacher asks you to plot the point 8. Let me get myself a little bit more spell. Let's plot the point 8, 7. So 8, 7. All right, so this is our vector x that we want to plot. Now, let's start normally. How would we plot this in the normal Cartesian xy coordinate system? Well, we would go to the right 8, and we would go up 7, and that would get us to our point, right? But wait a minute. This is, now we have this skewed graph paper, and we need to try to figure out how in the world do we graph 8, 7 if our basis vectors are different. All right. Well, just like a second ago, just like when I wrote the linear combination c sub 1 times v sub 1 plus c sub 2 times v sub 2, if indeed they are a basis, then that would mean that it should span all of our vector space, all of R2. We should be able to use, just like we can use these vectors to get to the point 5, 4, we could use these vectors to get to any point we want in R2. Now, we are going to do the same thing here. If these are a basis, if they are indeed a basis, then we should be able to use these two vectors to get to any point that we want in R2 space. More specifically, to appease our middle school teacher, we need to get to the point 8, 7 using our new basis vectors. So, but the good news is we're going to go back to the linear combination. So in this case, we would have c sub 1 multiplied by v sub 1 plus c sub 2 multiplied by v sub 2 is equal to any x, any vector x in our R2 space, okay? Let's plug in everything where it needs to be, and then let's figure out what the weights should be. All right, so that gets me to c sub 1 multiplied by 2, 1 plus c sub 2 multiplied by v sub 2. And the whole point is to get to the point 8, 7. All right, so in case it's been, in case it's been a second since you've done this, you definitely can play the game of trying to pick the scalar that distributes. Another way of doing this is just to simply take your three vectors, 2, 1, 1, 2, and you can go ahead and take your vector x and place them into a matrix. All right, and now we can just row reduce that matrix, which would give us, we'd have 1, 0, 0, 1. And as always, you can double check exactly what this should look like, but we should have 3, 2. And now what I need you to understand is really quickly, that's easy, right? Even our calculator can do all that lifting for us. I need you to understand what this means, right? So your calculator has this, let's say, in its viewing window, and what can we take from that? Well, obviously, we can take that c sub 1 is equal to 3, that c sub 2 is equal to 2. I get that. But now I'm going to go to the next page. So c sub 1 is equal to 3 and c sub 2 is equal to 2. On this next page, I'm going to rewrite this vector equation, but now I'm going to put a 3 here and a 2 here. Ready? Let's go ahead and write it. So we'll write it here. So this is going to be 3 v sub 1 plus 2 v sub 2 is how we get to the vector 8, 7. And here it is. This is what we need. So first, let me go ahead and plot v sub 1 and v sub 2. All right, so I'll go ahead and they're already labeled, but are plotted, but let me label them. So this would be v sub 1, and this would be v sub 2. Okay, and here we go. Let's see if we can understand. So the idea of how do we get to the point 8, 7 in our new coordinate system? Well, we need 3 v sub 1s. So we have 1. Let's go to the next one. There's 2, there's 3. So you notice that every scalar that you choose for v sub 1 is just either it's just moving up and down this line, right? And now what you can imagine is imagine parallel shifts running. So let me choose a different color and let me see if I can show you what I'm talking about. So this whole line, this is the v sub 1 line, right? What does that mean? What does that mean? That means that if all I gave you was c sub 1 v sub 1, then that just means that with that one vector and that one scalar, you can move up and down this line, but you can never get off the line. Okay, likewise, let's go ahead and plot out the entirety of v sub 2. So we have v sub 2 is running in this direction, and my apologies if that doesn't show up very well on that background. But the idea is still the same. If all I gave you was the vector c sub 2 and v sub 2, if that's all that I gave you, well, then what could you do? Well, you could choose different scalars, which would just amount to you moving up and down this line, right? You can go anywhere you want, but you can't ever leave the line. You would be stuck moving up and down the line. But now, as soon as we allow for you to be able to add those two vectors, that's when we can finally start to move to other points in R2 that we want to get to. The one that we really want to get to is this point 8, 7. So how do we do it? Well, since we need 3 v sub 1s, right? We need 3 v sub 1s. We need 2 v sub 2s. All right, and now what you can see is, let me label this. It's very important that I label this. So this would be 3 v sub 1. This here would be 2 v sub 1. This would be 2 v sub 2. And now from here, I'm looking for a color that might show up pretty good on that background. Let's try pink. Ready? From here, we can get to our point 8, 7. Okay. So what is the takeaway right now? So the idea is when you're graphing points, it doesn't matter if you're graphing XY points like you would graph XY points back in middle school. No matter what you're really doing is graphing multiples of some basis vector. Okay? you're graphing multiples of some basis vector. And now what I want to do is start to see if that makes sense. So after you've reached v sub 3, then you can see how 2 v sub 2 can move up and down this these shifts, right? These just moving parallel shifts to each other, and you can kind of see how you can get to the point that you want to be, which is 8, 7. All right, now what I want to do is label some things, okay? So hopefully it makes sense. Henceforward, if I say basis vector, then all I'm talking about is the basis for the coordinate system that we use to graph points in some vector space, okay? Now, when it comes to asking the question of is the following vectors a basis, that's something we'll have to practice a little bit more. But right now, I think you at least understand what I mean when I say basis. All right. Now, so what I'm going to do is I want to talk about what we call a coordinate vector. And notice the subscript that I'm using here has this B for basis, okay? So in this case, so let's remember, you wanted to plot the point 8, 7. But because this was a new coordinate system with a different basis, that's why all these lines look look slanted, they look skewed. Because of this, then what we have to do is let's go ahead and write what the point would be in our basis. So ready? Are you okay? So the point 8, 7 is the same as the point 3, 2 in this new basis. Does that make sense to you? Does that make sense to you? Like, look right up here. See, look, follow me. This point right here is the point 8, 7 if you're using that standard basis 0, 1, 1, 0. But this point right here, this is also 3, 2 in this new basis coordinate system. So that's the idea. That's the main takeaway. Maybe I can try to say the coordinate vector gives you the location of a vector on the new coordinate system. Are you ready? So if you have to write that, then write it. The coordinate vector gives the location of the vector on the new coordinate system. And this is obviously doesn't look like anything that we used in graphing prior. So this is a new coordinate system, and that's the location. All right. So where I want to go next is I want to focus on how do you actually show that, for example, I just came up with these two vectors. And I just assumed that they did form a basis for R2. Are you listening to me? I'm assuming that you can get to any point you want in R2 space, anywhere. I'm assuming you can get to any point in R2 space with these two vectors and set up as linear combinations with scalars. Right? I assumed it. I didn't show that that was actually the case. And now I want to get into showing how do you actually show that something forms a basis. I'm going to do this. We're going to do this a little bit differently. Okay, so that's where we're going next. Let me go ahead and read everything that I'm about to read. I've mentioned so far just a little. This is just a little bit more formal. So our theorem 7, the unique representation theorem. What does that say? So it says let B, right, equal the following vectors. And what we're saying is let these vectors be a basis for a vector space. All right, so we're assuming that they actually are a basis for a vector space. Then, for each vector in the vector space, there exists a unique set of scalars such that you can reach that point in the vector space by linear combinations of the bases. Now, it just so happens that the most obvious basis to choose is the one that you've been using all along. This is what we call the natural basis. So 1, 0, 0, 1. This is the natural basis in an R2 space. In R3, it would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. This would be the natural basis in R3 space. And the natural basis is very, very easy to plot in unit vectors, just like we've been plotting points all of our life. Oh, my sincere apologies. I'm going to have to cut this video early. My dog obviously sees a cat or something, but I will be back.